Okay, so here we have an FRQ, and as I noted in the notes for this, you actually know now how to solve this entire FRQ. Okay, so if you worked really accurately, reference your notes, and answered all 4 of these questions, based on what you know now at this point in your calculus career, you could produce like a full credit FRQ response here. You know how to do A, B, C, and now D. Okay. D is the newest thing. D is what we're going to go over here. But feel free to attempt the other ones as well. I've put some of these parts of this FRQ in front of you before too. Okay. So for choice D, we are looking to approximate the integral from 0 to 50 of v of t with respect to t with a Riemann sum. And this is going to be a midpoint Riemann sum. Okay. And we're going to use 5 subintervals of equal length. Okay. So this is somewhat tricky because notice we have 5 subintervals and we got a whole lot of numbers in the table. So you're like, it's kind of confusing what is what here. Let's start by figuring out the length of our subintervals. So 5 subintervals of equal length from 0 to 50. Well, that means 50 minus 0 over 10, or whoa, got ahead of myself there, over 5. So the bounds, the difference between the bounds over the number of subintervals, that gives me 10, right? So my subintervals are going to be 10 units long, okay? So what I'm going to do is I'm going to kind of make a table that only has my subintervals in it, and we'll see how this works out pretty quick. It works out nicely for us. So we're going to use from 0 to 10, 10 to 20. You can see where this is going, 30, 40, and 50. Okay, so my subintervals are going to be between these x values, or t values, I guess. And then what we want is the midpoint, right? And now you might be able to see based on the table how nicely this works out for us. We have midpoints are just given to us. So the midpoints are going to be all the multiples of 5 for our x values because they're between the numbers that I wrote for my bounds. So if these are t's, our f's of t we're going to use, I'm going to kind of write them between, are going to be 12. There, 15 goes with 30, 25 goes with 70, 35 goes with 81, and we have 45 goes with 60. Okay, so those are our midpoints, and we can kind of see, might line these up nicely here, but we can kind of see where these fit in. Okay. What we could imagine here is I'm making rectangles on my graph too, so you could also think about this graphically. I think I already screwed that up, didn't I? Yep. There we go. So from this, so these midpoints are what we're using. So I could draw this in the graph as well. So we're just finding the area of these rectangles. So what that would look like, it would be 10 times 12. The change in t every time is 10, right? So 10 times 30 plus 10 times 70 plus 10 times 81 plus 10 times 60. So I can factor out the 10 here. So the easiest way to do this would have been to just add up all these changes. Again, this is why Riemann sums of equal with equal subinterval lengths are so useful, because I can type this in my calculator very easily, right? Okay, so good notation would be to say the integral from 0 to 50 vt dt, squiggly equal sign, this, right? Squiggly equal sign because we're approximating. We don't know how to find the exact value of this. And then we're going to just punch it in my calculator. Okay, so what you get is 2,530. And then the units on these matter, because part of what they're testing, these are easier like FRQ questions, as long as you know like how to find each type of Riemann sum. But what part of what they're testing is that you understand the relationship between the integral and the function that's given. So we need to label this, and then notice it asks us to explain using correct units the mean of the integral. So I'll show you what that should look like, what they're looking for. So notice our b of t is in feet per second. The integral is the antiderivative. So if this is a rate of change of feet per second, this is just going to be feet, right? Just like the derivative of distance in feet would be feet per second, we're doing the opposite here. Okay, so feet would be our label, and then this is kind of our standard example is the velocity of the car traveling on a straight road. The integral, we tackled this at the beginning of the unit, right? The integral, the area underneath this curve, represents the total distance of the car, or the total distance traveled by the car. Okay, so is the distance traveled by the car, and then we're going to say a time as well, because I could easily give you like the integral just from 30 to 50, like a different subinterval. We'd get a different result, and it would have a slightly different meaning. So traveled by the car from time, what are we talking about, feet per second? 0 seconds to 50 seconds. So we're going to be pretty precise about the time as we're describing this. So always include your units on these Riemann sums problems, and then they'll often ask you to explain. And the explanation is going to be some sort of sum or total. We're adding up all of the changes over whatever bounds of the integral we are given. Okay. So there's a couple more for you to practice on your own after this. I'm going to give you feedback as you go. So go ahead and submit the formative, I guess I should say. The numerical answers will get marked right around for you, and then I'll give you feedback on your explanations via comments.